Okay, I think we can get started. Today we will introduce CaraNet for small medical object segmentation. This paper is published in 2022, MICAI. The innovations of these papers include the first, it constructs a loss for image segmentation at different scales. And those different scales those losses in these different scales will be responsible for the segmentation of objects of different scales. For example, small object and large object. The second innovation of this paper is that it achieves really high performance and the noticeable improvement when compared with the existing state-of-the-art models. For example, the highest die-score it achieves is 0.936. The first limitation of this paper is that so it introduced some techniques, but there were no ablation studies for evaluating the effect of them, basically how much they contribute to the final performance. The second limitation of this paper is that the performance on one particular dataset, for example, this Bright S 2018 dataset, is not good. It's potentially because of the extremely small object. We will show that later. I think the intuition for this approach to work is that those supervisions, basically those losses constructed at different scales, can encourage better segmentation of these objects of different scales. I think one potential direction based on top of this work is that we can generalize this approach for image segmentation with multiple class objects. For example, one particular image can have objects from different classes. Here in this paper, they only consider the foreground and background segmentation. Now let's talk about the training protocol of this approach. As I mentioned, it's a foreground and background segmentation task. The image is fed to this system, and it goes through some of these layers to get some feature maps. And those feature maps from different scales, they can be combined and then be fed to a partial decoder module to get a segmentation mask here. And this segmentation mask will be combined with the ground truth segmentation mask to calculate the segmentation loss. Besides this, there are also some intermediate predictions from some shallow layers. For example, at the layer F3, the feature map will go through a CFP module and then an attention module, and then corresponding prediction segmentation mask is obtained. And this segmentation mask is also combined with ground truth to calculate segmentation loss, similarly for the layer at F4 and F5. So for this segmentation mask predictions from these different layers, you can think of them as feature maps with different reception field. That means they can be responsible for the segmentation of object with different scales. So the final loss will be a combination of these segmentation loss at different layers. So at the inference, we can combine all the segmentation mask predictions from different layers for the final segmentation of the whole image. Ideally, each segmentation mask prediction is responsible for segmenting object of a particular scale. Since we have a set of segmentation mask predictions of different scales, ideally they should be able to segment the object with different scales. Now let's talk about some of the key components in the system. First is the first part is the partial decoder part. So this part, this model, basically this module, it takes 3 feature maps as input, and we do several levels of aggregation. For example, the first level, we do 3 aggregation. The first aggregation, it combines all the 3 feature maps. The second aggregation, it combines only 2 of the feature maps. And for the third one, it uses only 1 feature map. And for the second level aggregation, similarly, it can also take multiple feature maps as input, and then the third level aggregation. I think the purpose of this is just to get a better segmentation map. Now, about the CFP module, actually, it's a feature pyramid mod system. It can generate feature pyramids. For example, for feature map that is fitted to this system, we can generate a sequence of those feature maps with different channels. And for example, at this particular level is the first level, second level, third level, and the first level. So the first level has a feature map of this particular scale, and for the level 2, since it combines the feature maps from level 1 and level 2, so we have a final feature map at this particular level of this shape. It's an addition of them. And similarly for the level 3 and the level 4. So the final output of this module, like CFP module, is essentially a concatenation of all the feature maps from different scales. So here is a demonstration of this dilated convolution compared with the regular convolution. This dilated convolution, when it calculates the convolution operation, there is like one extra skipped pixel. For example, for image, there's one skipped pixel here and here. For regular convolution operation, it will focus on all the surrounding. For example, here when you consider like a 3x3 convolution operation kernel, it will consider only this center area. But for this dilated convolution with dilation rate 1, we have skip up 1 pixel in between, so that makes the reception field of this convolution kernel larger. Now about the axial attention, it's quite a simple concept. For example, here when you consider the images, you can treat for the head dimension, you can treat here I think they use the you can treat, for example, each head location as one particular token, and when you calculate the attention along this head dimension, you just calculate the attention of this sequence of tokens at different head location. Similarly, for this weight, for the attention along the weight dimension, we can consider each location of the weight as one particular token, and then we calculate the attention among them. For 3D images, we can do similar things. For example, for the head and the weight dimension, in that case, each slice can be treated as one token. Here, probably it's just like a tube that it can be used as one token. And this dimension is the channel dimension. Now about the performance, I think first the dataset is quite a challenge. For example, for all these dataset, some of the object can occupy as low as like 10,000, 1/10,000 of 10,000 of the whole image. For them here, and for images for object which can occupy 45% of the image, I think it's pretty big object. Yeah, for those objects, they are usually easy to segment, but for those small objects, they are usually challenging to segment. Now about the quantitative performance, I think the performance is not bad for this different data set. Especially for this particular set, it achieved really high performance, like 0.936. But for this other three data sets, it seems not that good. For this first data set, it's also not bad, I think. Now, if we consider the qualitative result and demonstration of the segmentation, I think the result is also not bad. Seems one thing I want to mention here is that this CaraNet is not really good at segmenting image with a really crowded small object. For example, for this particular image, it has quite some small objects here. And for all those approaches, they are quite struggling to do this task. Now, for one particular dataset, for the SPIE TS 2018 dataset, the performance is really low. It achieves only like a 0.6 something. But I think you can see the reason why. Seems for this particular set, all those objects they are extremely small. Yeah, and it's really hard to segment those tiny objects. Okay, that's all. Thank you.